He's a handsome dude, eh? Sorry. Yeah, I am indeed in December. I cannot believe it. 12/1/22. Unbelievable. Uh, so we're going to talk about three things. Only really, I think, one of them today, but the things that are coming up are called, the first thing we're going to talk about today are called factorials, which is very similar to the name of one of my favorite video games, Factorio, which has nothing in common. Factorials, combinations, and permutations. So we won't talk explicitly about probability here for a couple of days. We're going to talk about the mechanical things that go into now harder probability questions. So as we embark into more difficult probability, we can't get there until we understand how to find numbers of combinations and numbers of permutations. So on Monday, we'll talk about the other two, the second and third word. So a combination is picking a group of things out of a bigger group when you don't care about the order. So a good example of that might be something like, I don't know, you have 10 shirts, you can take 4 of them with you on a trip. You know, how many groups of shirts could you pick? We call that 10 choose 4, and the answer is immensely bigger than you'd possibly think. But the idea there is that order doesn't matter. And that's a different conversation if, say, 10 kids are running for student senate, and the elections that are held are president, vice president, secretary, and treasury or treasurer. And so in this case, order matters because, like, Kale being voted president, Brandon being voted vice president, and so on and so forth, that's a different order than if, say, Sam gets voted president, Kale gets voted vice president. You know what I mean? So when you have to take order into consideration, then we use something called permutations. And that's going to be more of a next week conversation. So mechanically, before we can get there, we have to learn about these guys, factorials. And they look like this. I understand that it looks like an exclamation point, and it's literally the same thing as far as how your pencil moves. You ever seen one of these guys before? Never. So what if I told you this, and I'll see if you can crack my code. What if I told you that 5 factorial equaled 120? Would you have any idea maybe from something long in your past as to why does that happen? How about this? 4 factorial is 24. 3 factorial is 6. 2 factorial is 2. So on and so forth. You would have no reason really to answer this question. I don't even know why I'm asking it. I just thought I would throw it out there. So any ideas? You're onto something good.
Oh,
yes.
5 times 4 times 3 times 2.
Yes.
4 times 3 times 2.
There it is. Sam has figured out what effect. Did that come from somewhere in your past, or did you just crack the code?
I cracked the code.
Good job, man. So the way a factorial is defined as it's that number times all of the positive whole numbers less than it. Notice I said positive because if we go to 0, then of course every factorial will equal 0. So in its expanded form, here's what 5 factorial would look like. 5 factorial is 5 times, now we just work our way down, 4 times 3 times 2 times 1. And grudgingly, I add the 1 in there because it technically should be there, but as we understand, it really doesn't serve much purpose. So that's what a factorial looks like when we expand it. That's what to expand a factorial is to write it out. So can you see now why 4 factorial is what it is? What would it be expanded out?
4 times.
Nice. Very good. And that's why that's 24. And then you can now see that 3 factorial is 3 times 2 times 1, which is why it's 6. And then 2 factorial is 2 times 1. And that's kind of what we need to know for now. So you ready to move into like utilizing them? So from now on, when you see the exclamation point, we're not asking you to say the number loudly. That's a mathematical notation reserved for multiplying that number by himself. No, excuse me. multiplying himself by all of the positive whole numbers less than him. Good. All right, so the types of math problems that we're going to be seeing are going to look like this. 6 factorial divided by 2 factorial times 3 factorial. And if you understand mechanically how a factorial works, then you just expand these out, and I'll show you some cool tricks on how to cancel stuff out. And this, you'll know why on Monday, why I'm having you do this, because the things that we're going to learn Monday, the little formulas that pop up, you're going to go, oh, yeah, that's what Thursday looked like. So, I'm going to write out 6 factorial. Sam, you had a question? You cannot. 6 factorial is 720, and 2 factorial times 3 factorial is like 12. So no, it doesn't work that way. Good question though, but no, totally illegal. Yes. So eventually, there's a there's a process here. Eventually, once you master the art of playing with factorials, then Monday I can teach you the formulas for combinations and permutations, and then eventually we can use what we know about combinations and permutations to answer probability questions. Today is all factorials. Yeah, Monday and Tuesday will be the permutations and combinations. Yeah. Good. So we won't talk about probability anymore today. We certainly won't even, I'll try not even to say permutations and combinations after that. We're just practicing mechanical stuff so that when Monday comes, we're not bogged down with all the stuff that we should have learned before. So let's get to it. The way this looks is I'm going to expand out 6 factorial. And so when I write it out expanded wise, it's 6 times 5 times 4 times 3 times 2 times 1. And you don't have to put the times ones. It's what I'm going to do. All right. And then on the bottom, I have got a couple of separated factorials. And as we established a couple minutes ago, you cannot like blend them. You don't get to, yeah, it doesn't work that way. So what is 2 factorial expanded? 2. And then what is, or just 2. And what is 3 factorial? 3 times 2. Good. And so what happens now is we're looking for things in the top and the bottom that are in common. It's like reducing a fraction kind of on steroids. And so if you look at the top and the bottom, you should see, and I'll assist you with some color coding here, that entire pack of numbers is identical to that entire pack of numbers. And the essence of reducing a fraction has always been that I'm going to kill things in the top and the bottom equally. So that pack 3, 2, 1 can eliminate that pack 3, 2, 1. Everybody okay with that? It's like you would reduce any other fraction. And then you might get stumped at this point and say, well, there's no more stuff that can cancel, but there actually is. And so I see that 2 and 1 make 2. And I then have kind of the pick of the litter, as they say. I can look up at the top and I see a couple of different numbers that can reduce with that 2. Obviously the 6 and the 4, right? Yeah. So just say I was to pick the 4, I can cross off the 2, 1 and say like, thank you for your service. Your services are no longer needed. I'm going to divide you by 2, and then I'm going to pick like this 4, divide him by 2, and he becomes a 2. And you see now the mission here is that I've made the bottom nothing. I mean, there's a 1 down there, but we don't care about that. So when all is said and done, we just take the surviving numbers, in this case, 6 times 5 times 2, and we multiply them together. What do we get? We do, in fact. So we see from this that 6 factorial divided by 2 factorial, 3 factorial is equal to 60. And that may seem like a totally inane, stupid endeavor, but again, it does serve a better purpose once we're ready to do that. Let me take a look and see. Yeah, I don't think you're going to encounter any troubles with this. I'm going to see if you can figure out a shortcut with me on this problem. Would anyone like to guess how big 10 factorial is? It's actually over 3 million for the record. It's like 3,628,800 or something like that. It's hard. I know, it's crazy nuts how big they get. Not like 9 factorial is one I had memorized a long time ago. 9 factorial is like 362,800 and something. So, right. And so if you bump up 1, then you add that extra number at the front end, right? And then just think about 11 factorial. Now you're like, holy smokes, we're talking like 40 million. I know, Jesus, indeed. Right, it happens quickly. So we're dealing with some really big numbers here. Anyways, if I wanted to do 10 factorial divided by 8 factorial, you could, once you know the trick, tell me the answer to this without a calculator in under probably 4 seconds. Does anyone know it? Another great question. You guys are asking really important questions. I don't know if you heard what he just said. You cannot reduce factorials like that. Like I can't take the 10 and the 8 and knock them down to great thought, but no. Again, massively illegal.
Oh, it turned into two.
What did you say?
No, it would
The hell did you get 90? Yeah, I want to hear what Dallas had to say just because he said it first, and you guys are both on the right track. How did you get 90? Oh, rats. There, I thought it was yours. Yeah, you got it legit without adult supervision. How'd you do it?
Oh my gosh. Well, like 8, like top 8, and you throw 9.
No,
So you have a 10. You have a 10.
I see it.
You take the 10 apart.
You cut them off.
Yeah. You take the 10 and 9 and cut it.
That's kind of how I've always tried to teach this. Is like with the yes. Good job. You guys are.
Oh yeah.
That's some good visual math there. And for those of you whose light bulbs didn't come on, I'm going to visually show you what your brain could have done for you, because I don't want anyone to feel left out. Here is 10 factorial. 10 times 9, and I'm sorry, I hopefully will not have to write this out again. So there's 10 factorial, and there's 8 factorial. And so in case that we all went too fast and you kind of felt like you got left out in the lurch there, you see now you do. And so basically the way I approach this is I start thinking about the top, and this is what you guys just figured out too, is as I'm doing the top, I start to think in my mind, okay, 10 times 9 times, oh, I should stop, because all the crap I'm about to write after 9 is going to be identical to all the crap that's on bottom, right? And so what winds up happening is if you understand how to do these, then you understand that you could have stopped right there, because you see the canceling happen before your eyes even have to see it. Good job, you guys that got 90. Well done. Okay, do you have any questions about this? Okay. If you, I mean, you understand a factorial and how it works, then there's not going to be a single problem on this page that's going to stump you. This is the only page I want you to do today. And then Monday and Tuesday, I say we start going down the permutation combination. It's really, I enjoyed that. It's one of my favorite things to teach because, like, how many people are in this room? Do you guys know? So would you like to guess if, say, someone from the yearbook came in this room and said, I want to take a picture of Mr. Ahern's third hour class, but I kind of want to know like what it would look like in all the different arrangements. So that means like you guys arranged in all the different ways that you can. Would anyone like to guess? If we were going to take a picture for the yearbook staff and we were going to arrange ourselves in order, it would be this big.
What the heck? You got to they all shuffled once. That's only 17. Yeah, you have to do 17 times 17 times 17.
So I enjoy always teaching this because if we 17 people were to arrange ourselves in all possible orders to take a photograph, it would take 355 trillion 687 billion 428 million 100,000 different photographs. And then let's think about this, like how many photographs do you think realistically we could take in an hour, in a minute? How many could we do in a minute?
If you smile,
No, because you can take 2 people in this room.
So we could just maniacally keep rearranging ourselves. Do you think could we reasonably say we could do 10 a minute?
No.
you can try.
If you start, what's fun about this is if you take this and say, okay, I can do 10 a minute, then that means I can do, we agree that we could do 10 pictures a minute by just rearranging ourselves. So we could do 600 pictures every hour. And in 600 if we worked constantly for 24 hours a day, that means we could do 14,400 different photographs every day. Okay, which is like, that's a lot of pictures to take in a day, right? And let's say we do that and we take that, and that's a day, and we want to know how many pictures we can do in a year. So let's take times 365. Guys, we're doing great. We could take, if we sat here for a whole year and did nothing but arrange ourselves differently for photographs, us, one class, we could do, this is great, 5,256,000 pictures a year. So now let's take, you know where I'm headed with this, don't you?
It's just gonna take you like 10 years.
No, I wanna know.
20 years. What if it's 5 million pictures a year?
It would take us over 16,586 years of us doing literally nothing but arranging ourselves for photograph at a rate of 1 every 6 seconds. It would take us almost 17,000 years. And if you take that and divide it by a human lifetime, which on average is, we'll say humans live on average around 80 years, it would take us 207 full human lifetimes just to take all possible photographs of this one flipping class. So I like teaching